This is the third presentation in the series Economy, Energy and Power. In this presentation, I wish to say and present to you some aspects of sizing of hydropower plants. Now, sizing here means the installed capacity, the plant factor of a hydropower plant. The first question is or would be, why does a hydropower plant needs to be sized? This is because hydropower plants have a wide variation in plant factors. You can have hydropower plants with plant factors of about 10 to 20%, say a lake in the Swiss Alps lying full of water to be dispatched when the system needs the power for a short period to stabilize the system, for example. Also, and on the other hand, you will have hydropower plants that have a plant factor of about 70 to 80, 90%. These hydropower plants on irrigation canals where if water flows the whole year around, then you tend to have a very high plant factor for these plants. Now, before I go any further, I would first like to point out that the cost of generation, the cents per kilowatt hours, is a very poor indicator of the economic value of a site. This is so because of various reasons, and no decision making should be taken or made on the basis of cost of generation. Even when you are sizing a plant and you have the plant laid out for different installed capacities, you should not compare each option on the basis of cost of generation. Why is this so? Because the hydropower plant generates power which has three separate components. All three are valued separately. Now, when I now speak from here onwards, I will be referring to medium-sized high-head hydropower plants. Although what I am about to say, what I will say, also applies to all other hydropower plants, but generally, for the sake of simplicity, I have chosen to only address sizing of medium-sized high-head hydropower plants. Why I have chosen medium-head high-head plants? Because these are usually on tributaries of main rivers. These are very steep, where storage possible is only meant for daily peaking purposes. That is, the plant is able to generate power in lean periods. For 20 hours, water is collected to be dispatched in 4 hours. The idea is to serve the peak demand portion of the load curve and supply power for the other segments of the power curve if possible. Now, for economic analysis of a hydropower plant, I have, in my previous presentation, I have presented some indicators and some methods on how this should be done. The only thing I would like to add here is that cost of generation is a poor indicator of the economic value or worth of a site, of a hydropower site. Now, economic analysis is carried out by various methods, but we will here only refer to the net present value method, which simply stated compares the present worth of all costs and present worth of all benefits, and if the benefits exceed cost, then the site or the investment is deemed as economic. That is, the net present value, the present value of all benefits should exceed the present value of all costs. Now, how should you the one other aspect I have covered this in my previous presentation on how to carry out economic analysis of hydropower plants. There are two main methods. One is the thermal equivalence method, and the other is the long run marginal cost method. Let us now, for this presentation, only concentrate on the long run marginal cost method. Why is that? Because the marginal cost estimates for energy and capacity are worked out for each voltage level, from generation level, 500 kV level, 220 kV level, 132 kV level, 11 kV level, and customer level. The medium-sized hydropower plants usually supply power at voltage say about 132 kV level. This would mean that the power supplied and the investment will avoid investments which would have been necessary to be made in the 500 and 220 kV EHV system, and this is a benefit which should be made available to this investment. I hope I make myself clear. And the long run marginal cost also has an estimate for peak and off peak energy. The estimates of capacity energy and peak and off peak energy can also be worked out on a monthly basis, but generally this is only done for peak and off peak periods. The other factor is that when you carry out economic analysis of a medium-sized hydropower plant, you should include transmission costs, because all transmission costs that are required to effectively connect the hydropower plant to the system should be taken as part of the project cost. But when you do that, then the benefit available to the plant should be at the voltage level at which you connect, say at 132 kV level. Now, how do we go about sizing a hydropower plant? But before we go to that, I will also introduce another factor, that when you size a hydropower plant, you size both the height of the dam and the size of the hydropower plant, the capacity. You do that because it is possible to keep on raising the dam height. There will be limitations from environmental factors and resettlement factors which will suggest that you should not go beyond a certain limit. But within that, there is a wide range of heights which are possible with the dam height. So you first optimize the dam height and you optimize the installed capacity for each of these options. So at the end of this exercise, you will have decided on the most economic height of the dam, and you will have decided on the most economic capacity and plant factor of the plant. Now, the benefits of a hydropower plant, as I have already presented in the my previous presentation, is firstly the provision of firm capacity. Firm capacity here means the 4-hour peak period contribution of the plant, which can be available 90% of time. This will be a fraction of the installed capacity. At times, this is even 1/3, one less than half of the installed capacity. The other two benefits are the energy off peak and peak energy. The peak energy is the avoided cost of a gas turbine, avoided operating cost of a gas turbine, open cycle gas turbine. And the off peak benefits or off peak value of energy is given by the cost of generation of a mid-ranked in the merit order, mid-ranked thermal power plant. Now, having said all this, let us now go to how we size this plant. What we do is we carry out analysis of various dam heights and capacities, and for each of this option we estimate the cost estimate, and we also estimate the energy and firm capacity made available to the system. For each option, you carry out an economic analysis, and the net present value, as I have already stated earlier, describes the economic worth of that option. The option which has the highest net present value then is the chosen option. How does this work? It works like this, that if you have let's say X capacity, and for X plus 5% or 10%, you will have the next step, the incremental costs from A to B should be less than the incremental benefits from A to B. That is, from one step to the next step, the incremental benefits should exceed costs. And as long as this happens, we keep on adding capacity to a point where this spread between benefits and costs comes to zero or goes negative. And at that point where benefits and costs are the same and there is no spread between them, that point becomes the optimized size of the hydropower plant. As I've already stated before, we optimize both dam height and the installed capacity or the plant factor of the plant using this method. This ensures that the investment will be economic, will be the best value, economic value for the system. Do not use financial parameters whilst doing all this. Do not use cost of generation as a decision parameter, as it does not capture the essence of the economic value of each of these options. I hope this is of some use to you. Thank you very much. In my next presentation, I will bring out some aspects of why hydropower development in Pakistan is in trouble, obstacles to development of hydropower plant. Thank you very much. Goodbye.